Hello again and welcome back to the abstract algebra videos. This is our fourth one and the last one in that first section. In fact, there's not a whole lot left to do in that section, but we will go ahead and finish it off in this video. Essentially, there are just two proofs that we have to do, or two theorems we have to deal with here. The book doesn't prove the fundamental theorem of arithmetic in this chapter, or in this section, so we're not going to either. I may skip past the proof when we get there as well, but for right now I do want to talk about both of these results. They're related. Euclid's lemma is used to prove the fundamental theorem of arithmetic, but we will prove Euclid's lemma today, and then I'll talk about the fundamental theorem of arithmetic, which is something that you will have sort of understood for a long time and probably almost think of as obvious now, but I guess that's part of why they call it the fundamental theorem. All right, so to start off with, we're going to talk about Euclid's lemma. Let me zoom in here a little bit. You'll notice it says if P is a prime and P divides AB, so AB is a product of two integers, then P divides either A or B. So in other words, if we have a prime and it divides a product, it has to divide one of the two things that's multiplied there. You could even extend this idea. If P divides a product of any number of integers, then it's going to have to divide one of those integers. In other words, and this is probably the way to think of it in order to sort of understand why this works. If you write out a product, you can't break up a prime and put a piece of it in each factor, right? Primes can't be broken up that way. Their only factors are one in themselves, so that's why this works. But one interesting thing about this that you might not expect is it uses our earlier result on the fact that the GCD of a pair of numbers is the GCD of a pair of numbers can be written as a linear combination of those two numbers. So we will use that in the proof. So what I would like to do first here is to talk a little bit about how we prove statements like this. This is one that you'll have seen in some sense a lot before as an if-then statement. So let me go ahead and put some notes over here. Let's make this red. So one part of this you'll be familiar with. For an if-then statement, you assume the if part and use it to show the then part. So that is one of the things that we're going to do here in this proof, and all of you have had proofs before, so that's not going to be anything new to you. You've all proved if-then statements many times. But there is one other thing in this that you might have proved less often, and that is that this then part, we have a either-or statement here. P divides either A or B. So what I want to talk about there, and I think I'll have room out here, is how we prove an or statement. So to prove an or statement, what you do is you assume, one of the two is not true, then show the other. And you might look at this and you might think, that sounds a little bit like proof by contradiction. And it is like that for a reason. You can actually kind of rephrase this as proof by contradiction. So both of these things here, how you prove if-then statements and proving or statements, these are notes that'll work for theorems in general. Okay, so let's get started on this, and I'm going to go ahead and start us off here for a couple things. We're going to use these if-then and or statements to sort of set up the outline of what the proof is going to be. So if you want to, I think now might be a good time to pause the video and figure out what you would want to say to start with here before you get into figuring out how we're going to get this result, because there are large pieces of this that you can just sort of fill out. So go ahead and pause the video and see if you can figure out the first 2 or 3 lines of this proof. Okay, hopefully you got somewhere pretty good on that. Let's see, don't need that bold anymore. Okay, so here we're going to start our proof. Now, remember here again, we're starting off with an if-then statement, so we want to assume the if part, which is convenient because it is right above where I'm starting here. So I'm going to say assume, first of all, P is prime, and that P divides AB. Okay. Let me make a little bit of room there. Okay. All right, I think that'll do. Now, so that's where we are to start with. Now, there are a couple of, sorry about the running, that's Loki and Lee for chasing each other around, and that will happen on occasion. Sorry about that. So what we're going to do here is we are going to say, we're assuming that P is prime and that P divides AB, and we want to show that P divides either A or B. And this is where we get into the or part. But before we do that, let's actually say what we mean by P divides AB. So by definition here, since P divides AB, that means there has to be another integer such that, so how does this work again? We have P divides AB. That means P times something else equals AB. In other words, AB equals PC. Nope. There we go. AB equals PC. So by definition, since P divides AB, there's an integer C such that AB equals PC. Okay, let's keep on going. So here, that is where we're starting. Now, at this point, we want to get into the or statement. Remember, we assume one of the two is not true and then show the other. Loki, quiet down, buddy. So we want to show that one of the two, assume one of the two is not true and show the other. So here we want to say P either doesn't divide A or doesn't divide B, and whichever one we pick is fine, it doesn't matter. So just because it's first, I'm going to say assume P doesn't divide A. So what that means then is P doesn't divide A, so A doesn't have a factor of P. Now, this is a little bit different than what this is going to mean in general, because here, since P is prime, that means the only factor A and P can share is 1. And we have another way to phrase that we've used already. In other words, I'm going to skip down here. GCD of A and P equals 1. So this is where we've gotten so far. We know that P doesn't divide A, and that means their GCD is 1. Now at this point, it might be useful for us to remind ourselves where we're going here. So we want to show then that P divides B. Okay, so that's where we're going from here. Now, I'm going to give you a chance to pause this again, and what I want you to pay special attention to here is this statement right here. GCD of A and P equals 1. We have a result that is going to allow us to use this GCD of A and P equals 1 and get something that's going to help us here. So I want you to pause, look through what you have, and figure out how that might help us. Okay, if you're back, we can go ahead and progress on from here. So, the result that we had last time, so since it doesn't really have a good name, I'm going to say from a previous theorem, but it's that theorem that the book calls GCD as a linear combination. We know that since GCD A and P equals 1, there are integers x and y such that ax plus py equals 1. Okay, so we have that now. Now, remember, we're not interested in whether P divides 1, and at this point we're not even interested in whether P divides A, because we've already said it doesn't. So what we want to do is we want to somehow show, again, that P divides B. So, what we're going to have to use is this statement here. Now, this is probably the trickiest part of this. If we have AX plus PY equals B, or equals 1, we can multiply both sides of this equation by B to get ABX plus PBY equals B. You can hear Loki scratching at the couch, can't you? He's going nuts. I don't know what's going on. All right, so I guess I'll have to play with him when this is over with. So multiply this to get ABX plus PBY equals B. So then what we want to do is we want to use this to somehow show that P divides B. Now you'll notice we're not there yet, but there is another piece that we've already got here that's going to get us a result that's going to show that P divides B. So again, go ahead and pause the video, look through what we've already got written, and find out what we can do to show that P is a factor of B. And I'll give you a hint. You'll notice we've got both sides of this are the same, so B equals this ABX plus PBY. Okay, so go ahead and pause this, and we will come back in a second. Okay, so if everyone's back, let's go ahead and show the trick here. Recall that AB equals PC. Then we've got B equals, so AB we can replace with PC, PCX plus PBY. And remember, we want to show that P divides B. How do we do that? We show it B equals P times some other integer. So we're almost there. So B equals P times, parentheses, CX plus BY. So B divides P, and we're done. Bam. And remember what BAM stands for? Badass Mathematics. That's what it stands for. Okay. You can put QED or the little box or whatever you want there, but that's the result there. And you'll notice this isn't too long of a proof. I probably overstated a few things that we could have just skipped past as well, but we've got this this result proved out now. Okay, so hopefully that makes sense to everybody. And now we'll get into the fundamental theorem of arithmetic. And like I said, we're just going to talk through this. We're not going to actually go through the proof of this, but I do want to explain how it works and do a couple of examples. So the fundamental theorem of arithmetic is essentially a theorem about, wow, Loki's really nuts right now. I don't know what's going on. The fundamental theorem of arithmetic is a result about factoring integers. And you'll notice here that when we start this, we say every integer n greater than 1. And you'll notice we say that this is either a prime itself, or it can be represented as a product of primes. So every integer is prime itself or a product of primes. This result and everything that builds off of this is the reason why we don't count 1 as a prime. At least part of the reason why we don't count 1 as a prime. Because if we did, we wouldn't actually be able to... a lot of these things wouldn't actually work. Like, first of all, we wouldn't say every integer greater than 1, but this next part would actually fall apart. Apart from the order in which they are written, this representation is unique. So in other words, once you write something as a product of primes, that's the only way you can write it as a product of primes. You can't write a bunch of different primes. You can rearrange the primes if you like, but you can't write it in a different way. So that is the fundamental theorem of arithmetic, basically. Like I said before, Euclid's lemma is used to prove this. The book gets into the proof later on, and we will get to that when we get there, but for right now, we're just going to use a couple of examples about it. Okay, so what I'm going to do here is come up with an example of a number to start with here, and then I want you to work on this on your own and figure out, is this a prime, or is this number prime, or is this number something that can be written as a product of primes? So that's what we're going to do. Let's start off with a number here. I'm going to have you all start with 113. Now, I know that's not necessarily easy, so you're going to have to do a little bit of work on this. You're going to have to pause the video and figure it out. Let me tell you one thing you can do to figure out factorization a little bit quicker is you can take the square root of the number. If the number has a factor, one of the factors has to, if the number can be factored into two integers, one of the integers has to be smaller than the square root of the number, right? Because either smaller than or equal to. If it's a perfect square, those two numbers are equal. If they're not, one of them is bigger, one of them is smaller. So that means you can square root this number, and you only need to check primes up to its square root. So let me put that down as a little note here. write this factorization in any order. We could write it 23 times 2 times 17, but apart from that order, these numbers aren't going to change. Now, one thing to note there is that since we're talking about the order not changing, sometimes it's worth just sort of, when you have a number and you factor it, writing it in what they call, let me put this here, canonical form. And what that means is write number, and when I say number here, again, I mean integer, n greater than 1, that wasn't right, as a product of primes and the last part of this here, how we make it standardized, is we do it in increasing order. And also, if we have primes repeated, we write them as powers. I know this video's got to be a little bit hard to follow when I'm zooming in like this, but the PDF looks better at the end. So with repeated primes, written as powers. You don't have to write every number's factorization in canonical form or anything. I mean, obviously, that is an option, but you don't have to. But it is sort of a standard way to write them, and it's awesome. So, for instance, how we've written 782 here, 2 times 17 times 23, they're in increasing order, so that is in canonical. The numbers, the factors, when you get them, they may not be in increasing order, so you might rearrange them to put them in canonical form. So an example here of something in canonical form, I'm not even going to figure out what the number is, but I'm just going to put it together here. So 2 to the 7th times 3 squared times 5 times 7 cubed times 23 times what? Let's say 59. That is an integer written as a product of primes, and it's written in canonical form because the primes from one to the next get bigger. That's really all a canonical form means. Okay, and so this is a result that you've already known, and we will get to a proof of it or talk about it if we don't literally prove it out, but I think that will be it for today, and this will be the end of that first section on the well-ordering principle in Math 405, and I'll see you back for the next video. I hope everybody has a great weekend.